Today, in our Colombian system, we have connected less than 100 megawatts inverter in high voltage, and we expect to have almost 8 gigawatts installed in the next 3 years. For example, in this slide, you can see the scenario in inverter 2023. We have a table. In this table, you can see the 3 main scenarios in Colombia for this year. We had a demand, conventional generation, solar, wind generation. They both are inverter, and the year 23 for every period, 4 for minimum, 12 for medium, and 20 for maximum demand in Colombian system. And it is important to mention that minimum and maximum is not possible to have a solar generation for this period. It is the second line. In the second line, it is possible. You can see the highest inverter generation because in this scenario are matched the solar generation and wind generation. It represents almost 50% of the maximum dispatch in Colombia for this moment. For this reason, this scenario must be included in every protection analysis. In this figure, in the left figure, almost 8 gigawatt generation that we are expecting. Most of them are solar, and this part is wind and this part is solar, and this is a distribution by high level, voltage level. Almost in distribution system, it could be 18%. Next, please. And this is a topology of DCN area in Colombia power system. In this area, we expected to have connected almost 4 gigawatts of inverters. 2 gigawatts of them will be in 2 main substations, Cosecitas and Colectora. And due to the massive connection of inverters in this area, it was necessary to include the expansion plan difference project to extend this area. And the green area, for example, this is an actual grid in GCM. GCM is very special because we are wearing 4 gigawatts. It represents almost 41%. This area, this green area is an actual green, and black is a future green. For example, we are expecting 5 transmission lines in 500 kilovolts, 2 substations. In each one, we are wearing almost 1 gigawatt. You can see that in the figure. Next, please. In this slide, I would like to mention some characteristics of the grid, GCM, and distribution system. I would like to mention that from the point of protection, inverters are characterized by low contribution of charge current during fault, contribution of positive sequence current, almost 0 sequency, but is close to 0, high sensitivity to voltage dip, modification of the current angles, and other. For the reason that the manufacturer of the inverter recommend to connect this equipment to strong grids around to 3 or higher. And in this moment, GCM area is characterized by a weak grid. The most of the protection schemes are conventional. It is based in 20 distance and directional overcurrent. This is very important because this area is far away from the main demand centers. This is located in the North Colombia, and the most of the transmission lines in this area are large. This is approximately 100 kilometers. I would like to mention too about the distribution system. As I show you the last slide, you are wearing a very important percent of this kind of generation in the distribution system. And it is important to mention that the distribution system was designed for unidirectional power flow. The flow typically is high to low voltage level, and it is important to mention that the distributed generation involves bidirectional flows. And this is very important and challenge for this voltage level. So the another thing very important in the distribution system is the protection scheme. They are basically no directional overcurrent. With this information, next please. With this information, we decided to propose you before with this information that I showed you, scenarios, topology, characteristics of inverter, protection scheme in this area. It is important to ask before starting which impact on conventional protection schemes should be considered and analyzed. What action should be implemented to improve the selectivity of protection scheme. In this way, we plan this line of work. The first one was characterize the grid, transmission and distribution, development and inverter model, and incorporate regulation. Actual regulation, complete result in other models, define operation scenarios and study cases, and propose solution and recommendation. This is the first part of this presentation. Thank you for your time. The next slide that we develop show you the model that you implementing to make simulation, and one show you the results and implementation. Thank you.
So, hi everyone. Let's start talking about inverter-based generation modeling. So, let me check this. Okay. So, in general, this is the let's talk quickly overview of protection system philosophy. So, at the first point, we have a physical system. Yeah, we take measurements of that physical system, and then we compare that measurements against a threshold determined by several criteria in order to determine whether the operation condition is normal or abnormal. So in the case where the operation condition is normal, we will continue operation. But in the cases where the measurements are abnormal, the process would be interrupted and the fault will be cleared. Now, these thresholds are the most important part in a system protection. So, how are the criteria determined? Well, first, it is required to know the physical behavior of the system under normal and abnormal conditions. Second, according to experience in operation and failure event analysis. So, due to the criteria is established according to system fault behavior, and we have to remember that renewable generation, due to its intermittence, needs a power electronics interface. This power electronics interface has a different fault behavior compared with a traditional synchronous machine. So what happens when we modify that fault behavior, including high amounts of renewable generation? Also, we have less experience operating this kind of resources. And this is why we need to evaluate what happened with conventional protection schemes technology. And This is our main purpose. So for achieving that general purpose, we need two elements. First, we need an inverter-based generation model which reproduces all these new dynamics properly. Second, we need protection relays to replicate the protection scheme operation. So for the first one, for this one, we find that there is a lack of generic EMT models. Also, the detailed manufacturer's models are given as a black boxes. So that's why we have to build our own generic EMT model fulfilling all the functionalities required for accurate short circuit calculations and protection scheme evaluation. Okay, for the second one, we find less issues because software packages usually include conventional protection schemes, and we also can use hardware in the loop to test real equipment. So this is the Energética work map. Green is for tasks done, and yellow is for in-process tasks. So at the beginning of the map, we have the development of an EMT generic IBG model. Then our model was compared with the inverter model used by EPRI, finding a remarkable similarity. Next, we migrate this model to the Opal-RT platform to check real protection device with hardware in the loop simulations. Also, we migrate the implemented model to RMS resolution in DigSilent Power Factory. This is important to spread these results with the industry because DigSilent is the most popular tool among Colombian agents. And then we start to check several issues like the impact of IBG on distance protection scheme and the effect on the measurement point in the distribution system. Also, we are working in new protection schemes and we are working on anti-ice landing schemes. All of the above with the aim to establish what is the best practice when we have IBG resources in the distribution system and transmission system, and then establish protection guidelines, for distribution system and for transmission system. So the first task in order to build a generic EMT IBG model was defining the best model type based on our requirements. This slide presents 3 inverter model types based on their different power electronic interface detail. So we have switch detailed, average controlled voltage source, and average controlled current source. The switch detailed is the most complete, is the most precise, but as a disadvantage, we have it requires tiny step size, less than 10 microseconds. And the average control current source, as advantages, has extremely efficiently, do not inject harmonics and do not need control interface. It has a little disadvantages, but in our experience, disadvantages are very little important. So once we define that we need a controlled current source model, we have to check the functionalities required for reproduce all these new fault dynamics properly. So in this case, we have 5 functionalities. Grid synchronization, because we need a properly grid synchronization under unbalanced voltage dips. We know fault events mostly are unbalanced. And also we need to check short circuit ratio scenarios. Second, we need to establish the impact of suppressing negative sequence current for the protection schemes. Third, we need to implement the short circuit current limitation. And this is important because it has significant impacts on the reliability and sensitivity of current-based protections. Fourth, we need dynamical reactive power control to fulfill mandatory requirements. And 5, we need to check for write-through capabilities. These are the 5 EMT functionalities required. And here is a figure, the ATP implementation, okay? So let's start to talk briefly of each one of these functionalities. So the first one is grid synchronization. In this slide, we present the double second order generalized integrator frequency locked loop, DSOGI-FLL. Yeah. This synchronization methodology allows decomposing a three-phase unbalanced system in a three-balanced three-phase system as Fortescue transformation does, but in this case, in the time domain. So DSOGI-FLL has a better response to disturbances than conventional PLL according to the literature review due to the frequency change under perturbations are less abrupt compared with phase change under the same event. So it has a smoother response to disturbances. So here we have an example of the DSOGI performance. A single phase to ground here, look at this. A single phase to ground failure occurs at 50 milliseconds and it's clear at 150 milliseconds. DSOGI decomposes in a very smooth way the PCC voltage in a positive negative sequence. Here is the positive sequence, here is the negative sequence. Also, the DSOGI estimates the grid frequency, yeah, and estimates the phase angle of the positive negative sequence PCC voltage. So first one check. Let's go to the second one. First statement here. Synchronous machine constructive structure determine its fault current behavior. But on the other hand, the fault current of an IBG is determined by its control strategy. So they are different. And in this sense, IBG are more flexible, and it is necessary to identify the impact of different control strategies on protection schemes. Here we have an example of three different control strategies. First, positive negative sequence control. Second, balanced positive sequence control. And third, average active reactive control. Okay? However, these are not the only ones. In this case, in this example, a single phase to ground fault occurs. Check out this. The same PCC voltage, the same phase A short circuit, but we can see all three short circuit currents are different. Also, we can see the impact on instantaneous active reactive power injection. Here we can see the active power oscillations are concealed. Here we can see there are active and reactive power oscillations, and here we can see how the reactive power oscillations are concealed. Also, we can see how in the first and the third, there is negative sequence current injection. But in the second, balanced positive sequence control, there is a suppression of negative sequence current injection. So there are many control strategies, and we have to evaluate the impact on short circuit current and in protection scheme operations. From the last slide, well, we have different control strategies impact, but look at this. All these IBG strategies still be different compared with a conventional synchronous machine. So traditional scheme adjusted for protecting conventional synchronous system, they will surely be affected. As a particular fact, we can also see how in conventional generation, look at this, the failed current phase is the biggest one. But in AARC strategy, let me put for you little bit. In this case, the failed phase current is the smallest one. So yeah, it's very particular. Let's go to the next to check the third item, IBG peak current limitation, impact on short circuit current. Yeah, why this? Well, due to the limited rated current of the power electronic interface semiconductors, usually IBG power plants have integrated limitation current algorithm, where the maximum short circuit current is limited to 1.2 per unit. Is the most useful, most commonly. In the first row, we can see the short circuit current with current limitation for the three control strategies we saw in the last slide. And in the second row, we can see the short circuit current without limitation. Yeah, there is a major difference. So this current limitation is essential to check protection system performance and constitutes the main issue for overcurrent based protection. Okay, let's go to the 4. Okay, there is a regulation requirements, and due to this, dynamic reactive power control is implemented. This control block determines the reactive power compensation under abnormal voltage condition, establishing that for voltage perturbations, the IBG would work with priority. So when the PCC voltage is out of this dead band, okay, the IBG would be working in priority. So for sub-voltage conditions here at this point, the IBG will inject more reactive power, and for overvoltage condition, the IBG will consume reactive power. Yeah, the compensation would depend on the drop on rise of the PCC voltage. Yeah, here in the here in this axis, and is defined by a linear slope. The compensation is defined by a linear slope. On the right side, we can see the typical power injection behavior for synchronous machine. Because the grid elements are mainly inductive, when a short circuit occurs, the reactive power increases, here the green, and the active power decreases. So when we implement this IBG dynamic reactive power control on our IBG controlled current source model, we try to replicate this kind of performance. Okay, this kind of behavior. So here we present the active and reactive power set points as a function of the positive sequence voltage drop and the inverter control strategy. Here we have the 3 control strategies we checked in the last slides. So here we have the voltage drop start to rise, and then the reactive power set point starts to increase, and of course the active power set point has to decrease. Okay. Also, we see that the best control strategy to maintain power injection is the balanced positive sequence control. Here is the BPSC. So finally, the five functionality, and it is the fall right through IBG capability implementation. This implementation is according to the Colombian code, and in this example we can see a single phase to the ground that is unclear for more than 1 second. When the phase C voltage overcomes his own low voltage right through core, the inverter cut off the injected current in a smooth way. Check out this. The inverter cut off the current. So the full right through implementation and consideration is essential because we expect renewable power plants to stay connected under fault conditions, supporting the system and the protection schemes, clearing these fault events before fault right-through capabilities be overpassed. Okay, and this is the last one, yeah. For the IBG model implementation, we try to be the most computational economically possible. So here we present the controlled current source model performance at initialization and time step requirements. So first, we implement here at the left, this is the initialization. So we implement a soft current starting block. Check this soft starting. Yeah, to avoid high overvoltage for the initialization stage. These overvoltage are clearly unreal. So this soft starting and the DSOGI initialization behavior allows the model to smooth start in less than 50 milliseconds. Usually 50 milliseconds is a pretty short time for EMT models. Second, we check the time step requirements here. The table presents the average error for the current waveforms for the same fault event simulated with a different time step size. Here we highlight that the implementation model can work with a time step of 100 microseconds with errors below than 3%. Here. So, usually 100 microseconds for time step size in an EMT model inverter-based generation is a pretty large time. Then, as I told you, in the Energetica world map, we make a comparison between our model and EPRI model. Yeah, EPRI is a very respected research institute. So, in this exercise, we use a study case. The study case is presented here, and the fault events was using these considerations: location at the 10, 20, 10, 50, 90% of the line, 4 types of faults: single phase to ground, 2 phase to ground, 2 phase isolated, and 3 phase, different fault resistance from 0.1 to 20 ohms, and 2 IBG control strategies, BPSC and PNSC. Okay, in this case, we compared the operation of the protection scheme displaced at each bay of the line 1. Check out this. Here we have a protection scheme, distance protection scheme with a teleprotection POTT and overcurrent, ground overcurrent with directional comparison at each side of the line 1. And the result of this exercise has a good percent of coincidences. So EPRI and Energetica matches in 82% of the fault cases. And in the cases that we don't match, the fault location mostly was 90% of the line. Here we can see how EPRI usually for that location, for location 90%, operates in zone 1, but Energetica operates in zone 2 with time acceleration given by POTT teleprotection. So at the end, the results were satisfactory. Also, there is a bias in this exercise because not only the inverter model was evaluated, but also the digital relay model. Okay, there is the Opal-RT implementation architecture where we check the voltage and current waveforms in an oscilloscope. This allows evaluating of real protection schemes, a real protection equipment. And well, we achieve a satisfactory implementation and simulation of our model in Opal-RT platform. Okay, highlighting that average computation time was close to 3 microseconds, and taking into account that we make the simulations with a 60 microsecond time step, the model implementation was economically, and there is a significant space to implement a bigger test case. Also, well, we can see here the voltage, the three-phase voltage and three-phase current from the oscilloscope. Also, here we have the RMS DigSilent implementation in DigSilent simulation language called DSL. This implementation was carried out controlling a static generator. Here we can see a static generator, and contains the same functionalities except for the grid synchronization, because in RMS resolution this is not required. Let's see the results for this comparison. We achieve that in steady state the errors are below than 3%. So here, let me check this for you. Here we see the comparison between active and reactive power. Red are EMT model, black are RMS model. Then we can see here the voltage by phase, per phase, and the current per phase. So in steady states, the results was very, very similar. So also, we find that the EMT model takes between 15 and 22 milliseconds for transient stabilization. This migration was successfully and has allowed us to analyze the effect of IBG generation, IBG, in more cases and more scenarios, remembering always that DigSilent is the most popular power system simulation tool here in Colombia. So that's all of inverter-based generation modeling, all the steps that we have made, and we start to the impact in conventional protection schemes in transmission system with Juan Fernando Piñeros. Thank you.
David, thank you very much. Are you listening me well?
Yes, Juan.
Okay, David, I will request control. Okay, I think I had it now. Good morning again. As I'm Juan Fernando Piñeros, as Laura was telling, I'm working together with Laura in the Colombian power system operator, and we are now to talk about the impacts of the conventional protection schemes in transmission system according to the studies we are doing in this project. Okay, first, this is the case, the base case we have. Important to say is this is the area Laura was presenting to you. And important to say, we have this area connected to two main links with the power system. The first one is Ocaña, 500 kilovolts. This is the first link. And the second link to this area is the substation Sabana Larga, 220 kilovolts. As you can see, it's a network with 2 points, and the substation will have mainly the connection of inverter-based generation will be Cuestecitas, is the substation I'm pointing here. And now I will show you the detail that I will use to present you the results. Then we are focused in the simulation of Cuestecitas mainly. Cuestecitas is already an existing substation in the 220 kilovolts, but will be a new substation in the 500 kilovolts level. And this level then will have the connection of the generation Laura was describing to you in the section of scenarios. And here we will have the substation Colectora Laura told you, 500 kilovolts with this level of inverter-based generation. And as well to this bus bar in substation Cuestecitas 500 kilovolts, we will have this level of generation. We are now then focused into analyze the performance of this distant protection relays here in D1. I will reference all the time that like D1, and we were simulating internal failures in the lines these relays are protecting, and as well some external faults here in this external adjacent line, Cuestecitas Copay. And we were as well doing some failures, some faults here in the another level of voltage at substation Cuestecitas 220. Okay. Then let's go to see what are our findings. The first one is very important. Is we with this simulation are observing that with inverter-based generation, they are doing a different fault impedance trajectory if we compare with conventional synchronous machines. Then this is a very important first result. When we have inverter-based generation and a relay protecting the lines are connecting this generation with the substation in the transmission level, then the impedance trajectory are when we increase the resistance of the fault here in blue 1 ohms or orange 5, yellow 10 and 20 and so on, the behavior of the final point of the impedance is in a way a vertical behavior. If you remember, when we have conventional power generators, they could have a trajectory, but with a little bit at an angle, and then normally we solve these problems with an angle as well in the relay. Yeah, but now with inverters, we have a really vertical behavior, and of course, some incursions we will have, and this is a problem. And we were testing with a control mode, a current balance control mode, and as well constant active power control mode. We observe the same behavior, and this is very important. Then the performance will be different. And we were talking before about a single phase to ground fault in the adjacent line. This is very important because we are not having any failure in this case at the line protected. And then we are tripping in someone for an external fault. It's very important. Now, as well, in the another voltage level, we were observing in the case of to do a double phase insulated fault in Cuestecitas 220 kilovolts, 5 ohms. We observed that with conventional generation, there is no problem. I mean, as we are used to, the distant protection will not see this fault, and this is the behavior we are expecting. But you can see that when we have inverter-based generation, then the impedance is coming from the right and is going inside. It could get inside of the distant protection characteristic. Then this is very important because this is different. This is something we are not used to, and we have to care because it depends on the dispatch of the system, the topology. We can have then these failures or these faults are getting in the distant protection. Now here we are simulating two-phase fault as well in the protected line, 50% of the protected line, and we use this slide to show you that when we have, for example, the mode of the inverter, the current balance mode, this is the behavior we are having. We show you before. In this case, it's an internal fault. Then it's okay. That is going in someone. Okay, it's working properly. But when we are using the reactive strategy control, then the problem is the impedance is going so far away of the capability of the relay to detect. Then here is the balance mode of the current. Here the reactive constant mode. Then we are not able to see. Then an important conclusion about how will be the distant performance is that it depends on the control strategy you are using in the inverter-based generation. Then it is important to say that we need really to have an accurate model of this kind of generation, because if no, you cannot check well or analyze well how will be the performance of the protection. And it's very important to have a detailed model, how will be the behavior and how will be the control strategy, because it matters very much. Another general problem we are observing is after we are going more than 5% location failure faults in the remote lines, in the adjacent remote lines, then in general, when we go 10%, 50%, 99% of the remote lines, we lost the backup of some 2 and some 3 of the distant protection. It means in the topology we saw, if we have a failure in, for example, in Cuestecita Scopei 500 kilovolts, in general more than 5%, then distant protection at D1, the location we were discussing, will not be able to see. And in general, we were simulating many cases, double circuits, even a fault in the double circuit line. We will have problems with the backup protection of the distance. Then we have to think about how we will provide a backup in these cases. Another topic we were observing is what happens when we do a variation of the dynamic reactive current support. Normally, we were starting to check with the value of key in 1. When we are increasing this injection of reactive current support in a fault, we observe that when we have a low resistant fault value, the change is not so much. It means it's not important. If we have a 0 ohms, 1 ohm fault, the behavior, or if you change the how much reactive support you provide during the fault, is not having a big impact. But when you are increasing the resistance of the fault, then is helping that you have a key value higher. I mean that you are doing a bigger injection of current reactive support. This is important, but of course you have to keep in mind that if you increase the reactive current support as well, you will decrease the active power the inverter is able to produce. And here we have to care about that if it's not important for your system that you are reducing during the fault the active power, okay, you can do. But if your voltage stability, for example, is depending of that you don't remove so much active power in the case of weak grids like we have now, then we have to find a good balance. Then we have to care about. Then here are some conclusions about the summary of the challenges of distant protection with high penetration of inverter-based generation. As I told you, depending on the topology, we will have in general, and we were running several topologies in general, problems with some overreachings we will have, and it's important to say it's not coming from up. The overreaching is coming from the right, and is arriving down like an incursion of because you have a heavy load. But the heavy load is because the inverter is adapting to the voltage, and if the voltage is low, of course, it is pushing that you have the power still going with low voltage, and this is generating that the overreaching is coming from the right, on the right side of the impedance loop. An important reduction then of the inductive reaching, that is normally the solution for these problems, is not working because as I told you, is coming from the right. As well, backup protection in zone 2 and zone 3 will not be available for most of faults in adjacent elements. This is important. Then we have to think about how we will provide a backup, because important to say, if we don't provide a backup properly, could be that then the inverter-based generation will disconnect because of low voltage fall right through. And this is very important, and we have to care about, because if you remove, for example, 1,000 megawatts of power because you have a failure, you cannot provide a backup, then you will have a big consequence and maybe a major blackout in this case. And of course, as I told you, the control strategy of inverter-based generation is really a key point to analyze what will happen with the distant protection performance. And here the message is we really need a detailed model of the inverter by generation if we want to be sure to see well the problems or the good performance of the distance protection relays in general. But of course, it's not applying only to distance protections. It's as well applying in general. If you put a line differential protection or over directional overcurrent, the same is applying. How to improve then the performance of distance protection according that we are observing in the scenario with high penetration of this generation IBG? The first point is we will have to reduce the resistivity region of zone 1. And as well, because as you saw in the graphics I was showing you, even if you reduce, it could be that there are some zones you cannot solve the problem because, of course, you cannot put that setting of only 1 or 2 ohms for the resistivity region of zone 1 because then you kill the dependability of the protection. Then, because of that, we are observing that one possible solution could be that zone 1 will require timing. Normally, you know, we don't put a timer or we don't time in this zone, but according to these behaviors we are observing of the impedance that is almost vertical, we have to. Some 2 stations should be analyzed to, of course, to increase the covering with and to work better in combination with teleprotection schemes. Why? Because if we reduce so much zone 1, then could be that we can compensate if you have teleprotection schemes or working with some tool like POTT, then we have to study to increase. Of course, if you increase some tool, maybe you have the challenge that then you have to check how much you can increase that you are not having the problems we are describing about overreaching. And a last point, conventional algorithms should be rethink or consider new features about distance protection. Why? Because as we are now checking, the behaviors of the trajectories of the impedance are not the same, then in a way we cannot use the same if we want to have a better performance. And one solution for that, for example, my colleague David, the researcher talking before, he's working in new strategy for detection of the location and faults by distance protection with high penetration of IBG. Then it's important this work he's doing because what is the problem? As you can see in this graphic here on the right, there are many failures in the that we can do in the adjacent lines, the remote adjacent lines. We are not able to see, or if you have a parallel line, we were not able to see because I was telling you we have problems in some 2 and some 3 distance protection backup. But then a possible solution is exactly to improve these algorithms, to do modification to these algorithms, and he is working on that these faults we cannot see, then with a modification, this is an example for a single phase to ground fault, before you were not able to see, and then with the modification you can see. Of course, this has to be tested properly, but then it's important because I will tell you again, if you are not able to provide a good backup for external failures, the problem is, remember, you have your low voltage fault rate through timing, and if you don't care about, then you can lose very big quantities of inverter-based generation. As well, we were working in some impacts of conventional protection schemes in the distribution system, because as well we will have a high component there. This is the first work we were doing on. It was about the effect of the measurement point in the distribution system fault detection with high penetration of non-conventional renewable energy generation. What is important here, it is that we were having some questions. How is the performance of voltage-based protection functions? And after the simulations, I will show you 2 main points we were having about. We now think it's clear. It is required to have low voltage protection function with measurement in every phase of the point of interconnection to be able to detect external failures. What does it mean? We need that if we have failures here in this network, this inverter can have the possibility to detect and to be disconnected, because if no, it could be there with the failure, and it could maybe be in a island condition, and then you don't have the clear of the fault, and in the worst case you can energize the network with high over voltage even. And we observed that in delta source systems, when this transformer is in delta, it is not possible to detect failures, for example, single phase failures with low voltage protection at the level of inverter. If you have here a delta connection, the low voltage protection function here will not work properly. And if you have a wide source system, it means when this is a wide connection winding here, you will detect that only the really close to 0 ohms fault failures. I will show you here fast. This was the network we were simulating, changing the connection group of this transformer here, delta or Y, and doing the failures here and in some part of the network, and checking what will happen about it. Then, for example, this is in the case the transformer is in delta. It's a delta system. If you have a single phase here in this point, in the point of interconnection, for example, you can check that in the level of the point of interconnection in the medium voltage, here in this case 13.8 kilovolts. Yes, you can see. But in the low voltage functions in the inverter level, you cannot see that. This is because of the connection. Of course, the vector group here and the delta system here. Then if you don't have a measurement point and a function connecting to that measurement point here, you will not be able to detect, and the inverter will not realize there is a problem. In the case this transformer is in a wide connection, sorry, here is delta, but it's a wide connection. If the fault is 0 ohms, okay, you can detect, and if you have a setting, for example, in 8.1 per unit to trip, this is the voltage, and you can realize and the inverter will trip. But if you start to increase the resistivity of the fault, 3 ohms, for example, here, then even if in the system you have a low voltage, for example, here, at the inverter level, for example, you will not realize if your setting, for example, is 0.8 per unit. Then it's very important, and we recommend that you have a measurement point here in the medium voltage network to be able to realize the situation and to trip in the right time the inverter, that the inverter is not energizing that fault, for example. And then another topic important is, are we prepared for sliding? Sliding in system we have inverter-based generation. Then the point there is we were simulating as well in this network cases, and we have, of course, the first case when the load of the network is much higher than the inverter-based generation you have. Of course, the low voltage will immediately trip the inverters, and there is no problem. When you have that the load is so less in comparison with the inverter-based generation you have in this network, of course, the natural result, you will have over voltage that we know by the protection of the inverters, and specifically in the DC bus of the inverters, it will be a tripping because the over voltage in DC, then this is not a problem normally. But what will happen then when you have a balance in the load you have here and the inverter-based generation, and you trip the main transformer that is connecting this network to the power system, you can have a balance. Of course, this balance will be able to keep depending on the PLL technology of the inverters. As we know, normally many inverters has a poor PLL system that is not able to keep tracking the system is as a result of the opening of this transformer. Then probably it will have a disconnection after some oscillation of the voltage. But if you have a good tracking system with the PLL, could be that the balance could stay there, and you have to handle this, that you don't have any problem or low voltage condition. And this is very important that when you have this case and the network is able to support some seconds, what will happen with the reclosings? Normally, some distributors system they have here. This is important. And then this work you can check online. This is the address we give you here. It's a paper we were doing for a conference. And another point is what will happen with the voltage stability in the distribution system when we have high penetration of inverter-based generation. Then we were, of course, checking. Some papers are worried about, because when you increase the level of inverter-based generation, in general distributed generation of this kind, you can have problems with the voltage stability. Why? Because remember, in general, they don't provide reactive power. Then if you are dependent only on that, and you have even events, you can have problems. Here, I will present you a simple simulation we were doing, which we have here a distribution network connected to our power system with a transformer, medium voltage level, with the 115 or 220 kilovolts level. We have some inverter-based generation that we are concentrated in these points, and then we do a failure here in this feeder, and then we are tripping this recloser or this reconnector in times are normal, 350 milliseconds. Then the transformer is 30 MVA, and we have an inverter-based generation totaling 20 megawatts. And then we do then a double phase to ground fault here, as I was mentioned, 2 ohms. Something normal could happen, and we clear this fault in 350 milliseconds. And then, because of the recommendations we have about, for example, low voltage tripping, that we avoid that the not conventional generation are stay connecting, then we have a tripping time 60% voltage, 200 milliseconds. And if you have in this network a load that is not only linear load kind of, and we nowadays a lot of power electronics in all the devices we have, then it means they can operate with low voltage and trying to consume the same power. Then in that case, as I told you, with these settings, we have a failure. We have the disconnection of the inverter-based generation after 200 milliseconds of the fault, and then here we have the tripping of this circuit part, and then this is what you can have. That then your network is not stable anymore, because the reactive power is requesting after the inverter-based generation are disconnected. And this is important, and we have to care about. Of course, if you have a really high interconnected distribution system, this should not happen, but this is something we have to think about. Okay, and this is our plan for future papers. We are now almost finished with this, the first paper, about all the models David was presented to you. And we are working as well in the papers about the real-time simulation model, as well of all the modeling we were doing for the teleprotection scheme that in ATP we were doing all. And as well as I was showing you now, the challenges in fault detection in distribution network with high penetration of inverter-based generation, and all other plans we have here. As you can see, we are worried about what will happen in the transmission system and in the distribution system. That is important to take actions to define what we will do. Important as well to comment that we will have differential line protection functions possibilities, but we have to think about the backup we have to provide, and it's very important that we are thinking to use functions that they are helping us to clear the abnormal conditions of the power system, that we don't lose the distribution system, or that we don't lose the transmission system. Thank you very much, and now we will open in the question session. Then I appreciate if Ernesto then is taking the control.
Thank you, Juan. Thank you, Laura and David, for presentation. We have several comments and questions for the presentation. I will start with a comment from Diego R. I think he's from Hertz. Now, he's stating that in United States, it's mandatory a specific EMT model for each IBG. This is mandatory since a generic model of EMT doesn't reproduce accurate the particularities of the models in these time steps, or yes. Also, I would like if probably Laura, who is more related with regulation, would like to comment from this, what is happening here in Colombia with the models that is required for the specific IBG plants. Laura, are you there, or I
Yes,
made the comment? Okay.
In Colombia, there is a regulation for inverter generation. It's a CRE 60. This regulation requires RMS model. It's necessary 6 months before the connection to deliver a preliminary model, and 6 months after the connection, a definitive model, but no EMTP. It's necessary a RMS model.
Thank you, Laura. So far in Colombia, we don't need it right now. I don't know if Diego, you want to make another comment or enhance your comment about the experience in the United States of this type of requirement. You can open your microphone if you would like to comment. I think Diego is not here anymore. So far in Colombia, we don't have it, but probably in the future, with all this study that we are making, we have to check if RMS is enough for this type of study, or in the future it will be needed a more detailed model from the providers. So we have another question. Let me check. There is something that was mentioned from Fernando, but probably you can make more comments from this. Carlos Alberto Garcia, he would like to know if grid lightning scenarios have been considered and how large was the test system. So probably Juan just show a little bit about that. I don't know, Juan, if you want to comment more about the scenarios and the plan of the future scenarios for lightning.
Yeah, if you want, David, we can go back a little bit, that we can show the total network. But in general, we were modeling the Cuestecitas substation and all the substation around, and we were modeling the inverter-based generation there here. We have this is like the zoom we have about this substation, but in the before slide, you can, as I was presenting, you can see the whole network. Because of time of the simulation, we were cutting and we were creating a network reduction in Santa Marta substation. I will request, sorry, David, I will request here control to point exactly that point there. Here, as you can see, we were creating here a network equivalent using by DigSilent the network reduction tools. And as well, we were connecting here in Copay the equivalent in general. Then, as you can see, we were modeling all these substations. You can see all this. And we were considering the scenario Laura was presenting, we call the P12, because it's the case, this is the time we will have the maximum point of the inverter-based generation. We were modeling then all the substations, generation connected here to this area, We have here the power plant Termo Norte, here Guajira 1 and 2, and these are the power plants we have in this area, together with the inverters-based new power generation here in Cuestecitas. And in the P12 as well, we were running simulation in the P04. It means in low demand conditions, where we have really weak conditions as well. But we can have as well some wind generation. Then we were considering that point because it's less short circuit and as well important level of inverter-based generation. If you have any doubt additional, we can answer.
Thank you, Juan. I don't know if Carlos, do you want to comment, or do you have any other question? Juan, you can open your microphone. Okay, so we'll move to the next question. If our friend Juan Jose Mora from UTP, where the inverter models are available. Right now, they are not available, these models. We are just waiting for our publication. And then the idea is to open them to make it available for general purpose. So, so far, we expect that it will happen in a couple of months, especially that. In any case, you can contact me. One, we can see if we can give a model prior we release it. There is another question from Juan Pablo. Sorry, I missed it. Juan Pablo, yeah, what do you want to add?
No. Sorry, no. You can continue. I saw a question and then.
Yeah, the Juan Pablo. Juan Pablo is asking, what do you understand as an exact converter model? Juan or David?
David?
Well, an exact converter model would be that model which includes the operation of the discrete semiconductors gates open closing via PWM methodology. So this is what we understand as an exact converter model.
Javid, and I think it's important as well to say, for protection purposes, an exact model is the model is giving you the behaviors of the currents the inverter is generated, or the voltage at the point of interconnection. This is very important because there are two points, or two range of times are very important. The transitions when the fault is happening, and the steady state of the fault, and how the inverter is putting there the currents or the voltage at the same time. Then it matters both, and you have to care that you have this properly, because there are several kind of like a black box models, but sometimes they are not accurate for the transition of the impedance, for example, because of how the inverter is recognizing the fault, going off temporarily and restarting to inject the dynamic reactive current support. Then accurate model, what we are talking about is that you have to have the right behavior of the converter. It doesn't mean that you have to have all the power electronic in the model behind, and you don't have to model the DC bus. No. In general, we are not meaning that, but we are meaning you have to have the right model that is giving you the behaviors that you can check what will happen with the current and the voltage at the point of interconnection, and in general, in the network, you have to evaluate the protection performance.
Thank you, Juan. We'll move to the next question. Brian is asking, do you think it could be interesting to provide new information to the relay, like IBG control mode, in order to change its parameters or algorithm? Juan or David that's working in.
Yeah, of course. Actually, this is what I implement in my thesis, in my master thesis. I will I will change a few parameters according to the control strategy. Even there is a set of parameters when we have a synchronous machine. So we can set the relay for protect different inverter-based generation control strategies, or even a synchronous machine, enhancing the performance of that protection scheme. Yeah, is correct.
Okay, there is another comment from Juan Pablo Gudelo. Hi, I'm starting my master's studies in Universidad Pontificia Bolivariana. I was thinking to base my thesis on protection schemes of distributed generation or protection of inverter-based generation, and this lecture has been very useful to me. So I'm asking if there is a possibility of have any kind of or support like information, or in better case, thesis direction, assessoring or support from any of the members of the whole group of Energética. Oh, Juan Pablo, so there is two types of asking here. The information, there are some information that will be public. So all the papers will be released. It depends what type of journal we will apply. Some of them will be open. But for the other, the direction of the thesis, UPB works in this project also. So we can make a contact through Gabriel Lopez. That he can put in contact with us and see. They are not working exactly in this objective, but we can probably make the interaction so we can see how we can interact. There are some other information that is not public right now. Some of the reports that we have there are not public, but probably we can make some arrangement if you link with the leaders of the project from UPV. We can make some arrangement there. There's another question, three more. How do you consider the equivalent of the grid? I think, Juan, you mentioned part of it.
Yeah, I would like to say about it that because the focus we have in this model, as you can see, we are focused into simulate what will happen in the substation Cuestecitas and around this substation. Then in general, we consider a static equivalent, a conventional static equivalent, because we are so far away of that point. And it's important to say as well that we are considering the power plants, the thermal power plants we have here, Termonorte and Guajira, as I was describing you before. And this is our main focus, because as well in protection times, as you know, we are focusing no more than 1 or 2 seconds simulation. Then, because of that reason, in this first studies we are doing, we have a static equivalent.
Okay. Yeah, I think the other questions are related to the same equivalent. I think. I don't know if Diana, you have any other specific question, but here is another question about Diana. Do they use a specific inverter model from ATP? Did they consider the model the inverters as voltage controls for current source? David, I think you can answer this.
Yeah, you can read for me again. I don't have access to those questions.
It was probably to me. Okay. Do we use a specific inverter model from ATP, or consider? Do they consider to model the inverters as a voltage control or current source?
Oh, actually, it's a controlled current source. It's an average controlled current source.
Okay, yeah, we developed all the model. It was in ATP. It was made by the program language and models, and it is implemented in models. when it was used in the Opal-RT, it was, you can remember, David, it was making Simulink.
Yeah, Simulink.
For in Simulink, and it was linked with the Opal-RT. They have a library to link them. So it is working smoothly. The time step is very small that we can achieve. So we think we will have good results when we use with real protection relays. Okay, so far, I don't know if there is any other question. If you have any other comment or question, you can open your microphone and you can ask if you like, or probably you want to make another comment in the chat. Okay, Juan Jose Mora, according to the previous answer, the average current model is not suitable for protection issues analysis.
Yeah,
of course it is. Actually, it is suitable. Yeah, because it reproduces the short circuit current very accurate for RMS protection schemes frequency domain. Okay. Yeah. Sorry. Yeah.
David, you can show. I think you can show the statement of the Sigro group about the model.
If I can interrupt.
Yes, Juan Jose, go.
It was because in a previous answer, Juan Felipe, I think so, mentioned that we need a very detailed model of the source, and I was a little worried because I was thinking that only switched converted model was available or was required for this type of studies. But I think that average model can be used also.
Yeah, I would like to clarify, David, if you accept. Yeah, I think it's important to say that there are many models. They are not having the features, for example, of the dynamic current support, follow right through, or even the control strategies. When you put all this together and you have a model that is having this behavior, then you have a set of possibilities to test. And I think my comment was more in the direction that at the end, of course, when you have the final equipment there at the place, the best is to have the models of these inverters. Yeah, because of that exactly, because we don't have models until now. Of course, you know, the manufacturers are really close with this. And then, of course, we were building a general purpose model for protection analysis that is integrating several kind of control strategies, the reactive current, the dynamic reactive current support, a limitation of the current, as all what David was describing. Then in that case, of course, you can use for protection, but when, of course, you will have the project now there and you place the wind park, of course, at the end, the best is to have the model from the manufacturer that you can evaluate. But of course, for analysis, planning, for estimation, what will happen, of course, is valid. And even we were testing, David can describe more, but we were testing with EPRI. The model of the EPRI was even was having a validation with a real inverter. Maybe David can explain a little bit more.
Well, no, as Juan said, and as Juan Mora said too, well, an average model is very useful in protection analysis because these switch detailed models represents and injects all the inverter different harmonics, and mainly for protection scheme, traditional protection scheme, we don't need those harmonics. Actually, we make a low pass filter, and we delete all those harmonics that we can find in the tail switch model, but we don't have in average model. So average model is enough. Actually, when we compare with EPRI model that is more detailed than our model, the difference between the impedance trajectory was very slightly, and the steady state was almost the same. So for this case, for protection scheme, for those equipments who make measurements, make low pass filtering, and calculates to the nominal frequency RMS quantity.
Sorry, we are losing David, I think.
Yes.
Yeah,
Yes.
if you...
Okay, thank you, David. We have problems with the connection. I think with this, I would like to thank all the presenters today, Laura Budelo, David Sanchez, and Juan Piñeros, for the presentation. It's very interesting, this type of thing, and we want to share with you all the achievements that we have done, and there will be more in the next months. So probably next year we will have another webinar related with this. I will say that in 2 weeks we continue with these webinars. We will have the type of CIM, the Common Information Model. We will have guests from University of Aachen. We will have guests from Jülich Institute. Also, Siemens, we will present a study case in Colombia. And we will have also the study case of exam of the implementation of SIM. At the end, we will have a panel with all these and all the new strategy that we are facing with a common information model. So I hope you are really care from our social media and our webpage. We will provide all the information for this webinar that will be held on Thursday, Thursday 22nd, sorry, Thursday 22nd, 10 a.m. again. Okay, so thank you very much. Thank you everybody to participate in this webinar.